Hello everyone. In this video, I am going to talk about section 2.9 dot product. Starting with the definition of dot product. Dot product of vectors A and B is defined as A dot B equals AB cosine theta. Left hand side of this equation, the A and the B here, they are vectors. Vector dot product of two vectors. And then the right hand side, this A and this B, they refers to the magnitudes only. So it's magnitude of A, magnitude of B multiplied by cosine theta. And that cosine theta, that angle theta, is the smallest angle between the two vectors and is always in a range of 0 degree to 180 degrees. Several characteristics about the dot product. The result of dot product is a scalar. Scalar means that we only have number. It can be positive. It can also possibly be negative as well, but it will only be a scalar, meaning number with magnitude but no direction. Also, number two, the units of the dot product will be the product of the units of A and B vectors. So whatever unit that you have for vector A, whatever unit that you have for vector B, multiply them together. That will be the unit of the dot product result, the result of the dot product. Over here shows you whenever you try to do dot product in between your IJK, just keep in mind that the dot product IJK with each other are always going to be zero. The dot product of IJK with itself will always be 1. So in this equation, it's remember in this PowerPoint that G always means the dot product. Unfortunately, in the PowerPoint, it's an image file. I couldn't update them. I couldn't simply get rid of the G and put the dot in there, but just keep in mind in this PowerPoint that G in our PowerPoint means dot product. So A dot B over here, because we have I dot J, J dot K, and K dot I will always be 0. The result for A dot B, when we writing the whole vector out with this X component, Y component, Z component for both your vector A and B, the only result that you're going to get is that one multiplied by that one gives you that, and I dot I is a 1. Okay, if you want to keep distributing I dot byj, look, I dot j, that's going to be a 0, so we're not writing it. Same thing, if you have the first term distribute to the last one, axi dot bzk dot product, it's going to be 0 because you have I dot k. It's the dot product with each other, not to itself. So moving on, same thing. Similarly, you're going to see the J component only, okay, and J dot J is a 1. That gives you AY, BY. And lastly, you will see AZK, BZK. K dot K is 1, and you have that, okay? Dot product, keep going. Using the dot product, we can use it to determine the angle between the two vectors. And this is a dot A dot B. For these two vectors in the Cartesian form, one can be found angle. We can use that to find the angle. Let's say I got two vectors, vector A and vector B. The angles between them is theta. We don't know what this theta is, but we can find out by using the dot product. So first we're going to find the dot product. You're going to calculate what is A dot B. What is the result of A dot B? And also we're going to use the magnitude. We're going to use the magnitude of A, magnitude of B, and multiply them together. Remember, our initial equation says A dot B equals vector A, vector B, A dot B equals magnitude only, AB cosine theta. Now, in this equation, if we know A, the result of A dot B, if I know how much this is, and if I also know what is the magnitude of A, what is the magnitude of B, and then we can find out what is the cosine theta is. Knowing the cosine theta, if you do a cosine theta inverse, that will help us find out the angles between these two vectors. So keep going using that equation, keep that in mind. And we're going to find a dot product being A dot B equals AX BX plus AY BY plus AZ BZ. This equation was derived from the previous page. And then we know the product of the two vector magnitude only. And then we're going to use theta cosine inverse A dot B divided by AB. So in this equation, right? So you will have cosine theta equals vector A dot vector B divided by AB. And then if I keep going, theta will be cosine inverse A vector B dot product divided by magnitude AB. So that's where this equation comes from. Now, be careful. What number that you're getting here will always be a number in between 0 degree to 180. So this less than. So in greater than 0 degree, less than 180 degree is what that is trying to show. There's a lot of funny writing in this PowerPoint. I will try my best to show you what they're trying to say to you. Okay. Next thing, we're gonna use dot product to determine the projection of a vector. So over here, we can determine the component of a vector parallel and perpendicular to a line using the dot product. Over here, let's see, vector A, we can project it into two different axes, horizontal and vertical. And we're gonna call the one vertical being the perpendicular, A perpendicular. And we're also going to call the one horizontal being the A parallel, or later in our notation, we use AP. So that P there means A parallel, or you can also call it AP, same thing in this problem, in this example. We're going to find the unit vector UA along line AA. Along, so this is your AA. This line right here, this line, horizontal line right here is your line AA. Okay, so if you keep going. Find the scalar projection of A along line AA by using the dot product. So over here, this means A dot UA. Vector A dot UA. UA being the unit vector along the line. Okay. We know that A, if I want to keep writing, expanding this equation just a little more, that A is going to be AXI plus AYJ plus AZK, and you have dot product with a unit vector. Unit vector, you're going to have UXI plus UYJ plus UZK. Okay, so it's a dot product in between them, and then you can put them together, just like I derived before. The dot product IJK with each other will be 0. Dot product IJK with itself always be going to be 1. So when we're doing distribution, you will only see the x together, AX UX, AY UY, and then AZ UZ. So if needed, the projection can be written as a vector, A parallel by using the unit vector UA in the magnitude found in the previous step. So either AP or A parallel with two lines at the bottom, they both means A parallel. The scalar and vector forms of the perpendicular component, we can using the perpendicular by using, we know the parallel, we can use the Pythagorean theorem backwards, right? Pythagorean theorem backwards, but Pythagorean theorem 4 says A parallel square plus A perpendicular square will equal to your A overall square, right? That's our Pythagorean theorem. So being said, we're using it backward to find out what is the value of A perpendicular. And keep in mind that these are all vectors. Next thing is that over here it says rearrange the vectors. Sum of A equals A parallel plus A perpendicular. And notice that these are all vectors. This is vector addition. I'm adding the vector together. Parallel plus perpendicular gives me the diagonal of the vector. Let's take a look at an example together. So we have this force being applied at point A, It tells me the magnitude, negative 6I plus 9J plus 3K, and then overall in this much kilonewton, right? So it's a force vector in the air. And then we want to find the angle between the force vector and the line A. We want to find this angle theta and the magnitude of the projection of the force along the line AO. Step number 1, we're going to find the position vector RAO. So in other words, what is we know the coordinate A, we know the coordinate 0, right? So we're going to find the coordinate A right here, and the O, it will just be 0, 0, 0. Okay, so over here, 0, 0, 0. For your A is going to be, X value is going this way, so it will be this much in positive, so that's a 1. And the Y value is going this way, will be this much, so that's going to be -2 because it's going the negative direction of Y. And then the Z component will be that much. It will be +2. So this is my coordinate for A. And then in order to find the ROA, we need the ending point minus the starting point. So you're going to take that 0, 0, 0. So 0 minus 1, 0 minus -1, 0 minus 2. So this will give me the position vector, being the vector that passed through point A and point O, starting point O, starting point A, ending point O. Okay, ending point, subtract the starting point. The next one here is to ROA without that blue. This means I am trying to find the magnitude. I am trying to find the magnitude of your ROA. That's what we're doing, magnitude. And then using the force vector is -6 plus -6i plus 9j plus 3k. This is my force vector, and I'm finding the magnitude of the force vector. These are magnitude of the force vector. And then I will do dot product. This is not a G, it should be a dot product. F dot ROA. Dot product, I am taking the I and the I together. Okay, look, let me color code it. I and the I together, which is this part. And we're going to do the J and the J together. That's that part. And then we're going to take the K and the K together. That's that part. These together, that will give me the result of the dot product. Now, unit, remember we say unit, you just simply combine the unit of the vectors together. So you have meter and kilonewton. So you have kilonewton meter multiplied together. Okay. Now, same equation, you're going to use cosine inverse. On the numerator is the dot product. On the denominator is the magnitude of these two vectors. This doing cosine inverse will give me the angle between the two vectors, which in our case will be the vector F and the position vector go pass through A and O. That will help us find the angle. Next step is using the position vector to find the unit vector. Unit vector has the same direction as the position vector. So UAO, unit vector UAO, has the same direction as the position vector AO. But however, unit vector has a magnitude of 1. Put the unit vector and the force vector together, dot product, that will actually give me the FAO. So, in other words, what is the force being projected into the line that's passed through point A and point O? You may also use F cosine theta, like you project it as if it's just like a triangle over here. Okay, looking at this triangle, F projected into the line AO. You could do that too, since we calculated the angle theta from the previous step. But either way, they give you the same result. You give 6 kilonewtons. Example number 2, we have a force vector acting on A, 600 pounds, right? And we have 60 degrees and then 30 degrees projected, 60 degree is projected to the XY plane, and then you have another 30-degree projected to the from the XY plane to the Y axis. What we're looking for, find the components of the force acting parallel and perpendicular to the axis of the pole. So we're going to use dot product in here again. First thing first, position vector. What is the position vector going through point A and point B? Point A and point O. Point O is going to be 0, 0, 0. And then point A, your X value, since we're going to the positive X going this way, and that A is going negative direction of that O, so it will be this much, which is 4 feet. So it's -4 because it's going toward a negative direction of x-axis. And then y is this portion, okay? which will be 4 feet positive because it's going positive direction of the y. And then the z component will be this much, or this portion, which is 2 feet, negative 4, and 2. Okay, position factor pass through O and A. Starting point is your O, ending point is your A. So we're going to use ending point minus the starting point. So whatever you have on the A minus the O. So you have negative 4, 4, and 2. That's where you get that position factor. And then this step is going to be the magnitude of that position factor. And then this one right here comes from, hopefully you already know it without even me talking about it. It will be the position factor OA divided by the magnitude of OA. Okay, so basically you take the first row, negative 4i plus 4j plus 2k, divided by the magnitude 6. That will give you the unit vector. That will give you the unit vector with the magnitude only 1. Next thing is we're going to talk about this force vector. We have our force vector and we need to project it twice. First time, the force vector, this one right here, we're going to project it into the xy plane. So it's this one, F into the xy plane. Okay, so in this triangle, in this shaded red triangle, 90 degree is right here. 600 is going to be the hypotenuse, and then the other two sides are the two sides of the right triangle, right side of the triangle. So if I call this one the F prime, okay, and then 60 degree right here, this is your 60 degree. What it means is that F prime is going to be F cosine 60, or F cosine, hold on, F cosine 60, and hold on, wait a minute. Yeah, F prime is going to be F cosine 60. And then the vertical component, let me get rid of that. I meant to say the vertical one is going to be the Z component. Okay, vertical is this portion, which is along same direction as the Z. So it's the Z component will be F sine 60. Okay. Now, F prime can keep going further, and let me project it a little further. So you're looking at this rectangle right here. Okay. And let me draw that rectangle in the 2D notation. F prime right here. Okay. This one is going to be the Y. This is the Y axis. And this is the actually x-axis going down, coming out of the paper. So to be consistent, your x is going this way. Okay, so when I projected the f prime, you have fy is this one, and then your fx is this one. So to get fy, and we know this angle is 30 degree right here. Okay, so I'm looking at this green shaded triangle, which is this one there, the same thing. So Fy is going to be F prime cosine 30. And that F prime is going to be F cosine 60. Plug it in. Cosine 60, cosine 30. And this is positive. Same thing, we want to do your Fx. Fx is going to be F prime sine 30, but negative, because I'm going the opposite direction of the positive x. And then plugging the F prime is going to be, so you have that negative, F prime would plug in from up here, F cosine 60, and then multiply by sine 30. Okay. Anyway, that's where all this part right here, what I just derived is this part right here. We get the ijk component, which is the xy component of this force F along the direction of x, direction of y, and direction of z. And I let you put into the calculator to verify if all the results are correct over here. And it keep going. Once I have the F value, I do F dot product with the unit vector OA. That will give me how much force is being projected into the same direction as OA, the line that passed through O and A. And then over here, it's a little funny looking, but hopefully you get it. You should get it figured out. What are they trying to tell you? You have dot product, which is take this I and the unit vector I, that gives you this part, which will be negative 150. There's a negative here. I kind of covered it when I circled that. It's negative 150 times negative 2/3. So this is trying to say negative 2/3. And this is the I component. And then J component, I'm going to go with orange. You have 259.8, and that's the J component. This is 259.8 times 2 over 3, and that's my J component. And similarly, we are going to do our K component, which you have negative 519 and then 1/3. So this is trying to say 519 times 1/3. That is the J component. Okay, hope that color code helps you. So dot product, again, I trust you. You can put it in the calculator to verify if it's 446 for the final result scalar. So overall, you have your F 600, and you also have the F parallel being 446 from the previous slide. And we're going to use the Pythagorean theorem backwards to find out the F perpendicular, which come out to be 401 pounds. No problem. Okay, so we have force 300 Newton acting on this bracket. We want to find the magnitude of the projected component of this force acting along line OA. And again, we're going to go with find out what is the coordinate of O, which will be 0, 0, 0. Find out the coordinate of A. So let me help you. X is along this direction. So how much X do you have along the X direction? And then your y, it will be this much. So the y is more obvious, 300 millimeter. And then you have the z component is how much it's being elevated vertically going up. You do need to play with this 300 and then the angle 30-degree right here. And we're gonna go take a look. Okay. So first thing first, we're going to use this ROA, find out what is ROA. Again, like I said, you need the O, which is 0, 0, and you need the A. Okay, so this 8 over here, slightly more complicated. You're going to break that 300. Let me put it in the 2D notation. So from this point, so I'm drawing this one to A. That's called its point P. So PA is over here. So we're going to project that P and the A into the 2D. So because this one is 300 millimeter, and we know that in between this is the z-axis, this one is going to be the x-axis. The angle between that PA, the 300 millimeter, and the z-axis, this angle right here, as marked, it's 30-degree. And using that 30-degree, you can do your sine, you can do your cosine to find out how much. So meaning this side is going to be 300 sine 30, which is 150. Feel free to put in your calculator because sine 30 is 1/2. 1/2 times 300 will give me 150. And then over here, this end is going to be 300, or the z component, or this end, either way, the same thing, 300 times sine 60, or you can do 300 cosine 30, either way, same thing. Or this will be 300 square root 3 over 2, or I'm writing it going up. It's a little funny, but you get the idea. It will be 150 times square root 3. Okay, and then plug into the calculator. Now, this is not the actual coordinate of your A, so don't forget to, for your, this is the x component. For the x component, don't forget to add that 300 millimeter. So in other words, the x component of that coordinate A will be 300, which is this part, plus an additional that part, right, which we calculated, which is right here, 300 plus 150, which is 450. And also it's going to be negative because your positive x going this way, but the A is going the opposite direction of the positive. That's why you have a negative 450. And then the y value, you can read it from the graph, which is this part, which is 300 millimeter. They put it in the meter. That's why it's 0.3. This one is 0.45. And then later you put this one into the calculator, 150 square root 3. That will be the z component. Put that into the calculator and then convert it to meters. That will give me 0.26. Hope that helps you. This is the vector, and then this one right here is the magnitude of the position vector, and then this one, the u, will be the unit vector passed through point O and point A. Okay, and then we come back to our force. Our force, again, with all these angles, we're going to project it twice. Number one, we're going to project that f prime into, sorry, we're going to project that f into f prime. That's our first step. So in this triangle, since they use red, let me go with red. Over here, you have that triangle. You're going to project that f prime into f sine 30. Okay, so your 30 degree is right here, meaning this one is 30 as well. So f prime is the same thing as this one, either way. So f prime is going to be f sine 30. And then keep going. We're going to project that f prime one more time. If you want to write it in the 2D, project it to the 2D, let me show you a little bit. So you're going to project that f prime into fz, and then down here you have fx. Okay, so other words, it's not too accurate, so but I'm going to say show it parallel to the x. So you have your f prime here, and then you have your fz, and you have your fx. The angle between f prime, not f1, my bad. The angle between the f prime and fz is going to be 30 degree. Using that 30 degree, okay, we can find out the fz equals f prime cosine 30, fx equals f prime sine 30. Be careful with the sign. Again, x, it will be negative. Okay, so now that plug it in, we know that f prime is 300 sine 30, so fx is going to be 300 sine 30 with another sine 30, or you can plug it in, which will be 150. So 300 times sine 30 is 150 right here, f prime, and then times another sine 30. And it's negative because it's going toward a negative direction of fx. So that's that part. And then the second part is your y component. Y component, when you project it the first time, we get it, right? So it's sine 300 cosine 30. So it's Fy, if you don't see it, let me use a different color. Fy, if you don't see it, when we project the F, this F right here, project it to F prime, the other side of it is Fy. Okay, so that's why you Fy with that 30 degree triangle, you get 300 cosine 30. And then the z, you gotta do, you up here, you plug in the f prime, which is 150 newton times cosine 30. So 150 newton times cosine 30. All right, plug in your calculator, get the force vector, and we can use our Pythagorean theorem to find the magnitude of this force. Later, we're going to do dot product, force vector dot position vector OA. That will give me a scalar, a numerical value. The units will be the product of the force and the position vector. Okay, and then using that, we can find in cosine inverse, find the angle between the force F and the position vector ROA. And if we, with that angle knowing, we can do a F cosine theta to find out what is the projected force along the direction of the position vector. You may also